Hello everyone. Welcome to another video. Now this time on Norton's theorem. So in the previous set of videos in my channel, we discussed Thevenin's theorem applicable to DC circuits. However, the theorem itself is applicable to both AC and DC circuits, but we have only discussed DC circuits. Now Norton's theorem is very much related to Thevenin's theorem. So if you recall, in my previous set of videos, I have solved a lot of problems related to Thevenin's theorem. Okay, so now in this last video, or in this one kind of dedicated video, I don't want to do a separate playlist for Norton's theorem, but this will be an individual video for the Norton's theorem. Now in this also I want to solve multiple problems, but before that let's see what Norton's theorem is. Okay, so Norton's theorem says a pair of terminals of a network, at a particular pair of terminals, the entire network can be replaced by a current source and a resistor in parallel. So look at this diagram. So there is a big network. In this network, this particular terminal is identified as A, and this particular terminal is identified as B. Now A, B, two terminals are identified in the entire network. Now this entire network can be replaced by a current source in parallel with a resistance and identifying A, B as terminals. So both the circuits will behave in the same way. In other words, if I connect a particular resistance between A, B, how much current will flow and how much voltage will be in this circuit, the same behavior, the same amount of current and the same amount of voltage, same amount of power, everything will be same when you come to this simpler circuit. So basically it is like a circuit simplification. So it's a complicated big circuit can be simplified into a simple current source in parallel with a resistance. So this is what Thevenin's theorem is considered. Now, but how to calculate, how to evaluate what is the value of INO and RNO? This INO, that is Norton's current, and Norton's resistance, are function of the entire circuit here, whatever it is there. So depending on the circuit parameters, these values have to be calculated. There is a procedure I will explain. So meanwhile, the Norton's equivalent circuit is related to Thevenin's equivalent circuit by this equation. So the Thevenin's resistance is exactly same as the Norton's resistance. So the same procedure, how you find the Thevenin's resistance, we use for finding the Norton's resistance. Now for the Thevenin's voltage, if you know Thevenin's voltage and Thevenin's resistance, then you can V by R you can do and find the Norton's current. Or if you know the Norton's resistance and Norton's current, then you can find the Thevenin's voltage. So it is simple, like it looks like an Ohm's law, V equal to I into R or V by R equal to I. So if you know any two parameters, you can calculate the third parameter. So and the R is common for both. So this is the thing. Now how does the equivalent circuit look like in the case of Thevenin's theorem? So if I go back, so here you notice on the left side we have a kind of circuit where 6 volts and 6 ohms, 3 branches are there at different values, and on the right side AB terminals are there. This is replaced by equivalent resistance in parallel with the equivalent voltage source. So VTH is 2.25 here and RTH. So this entire circuit has been replaced by these two elements, and then there is a 3 ohms load resistance which is common. So similarly, if I take another problem, this is the entire circuit. This entire circuit is replaced by one voltage source and one resistance. So like that, any circuit, whatever is a circuit, it can be replaced by one voltage source and one resistance in series. That is the Thevenin's theorem. Coming to Norton's theorem, it is nothing but you can replace the circuit by one current source with a one resistance. So that is the only difference. So we'll just solve some example problems. Now now what is the benefit of Norton? Why not only use Thevenin? So certain situations Norton will be beneficial and certain situations Thevenin's will be beneficial. So you should be able to recognize how to do that. That is what we will try in the example problems. So I'm going to solve one. Okay, this is not the first one problem. Second problem, 3, 4, 5 and 6 problems. So I don't have any further problems here. So I have taken the 6 problems to solve how to use the Norton's theorem. Okay, so again you can okay, so you can just If you want to particularly take each question separately and try, you can pause the video whenever I was showing that circuit, and you can try to answer it yourself. But now let me start my own answer, and we can compare your answer with my answer to check your understanding. So let's get started. So let's say the question is given like this: considering A and B as load terminals, find Norton's equivalent circuit and find Thevenin's equivalent circuit. Okay, so first let's see the first step is, okay, so step 1 is common, finding RNO, so Norton's resistance, which is nothing but Thevenin's resistance. So the procedure is same. All voltage sources should be short circuited and all current sources should be open circuited, and then find the resistance as viewed from the AB terminals. What is the resistance? So it's very simple. The circuit becomes like this: A and B, and then we have 2 ohms here and 2 ohms here. So here the voltage source has been short circuited and the current source has been open circuited. So the resistance is 4 ohms. So this is nothing but RTH or RNO. Okay, so this is simple. Now comes the second step. So in step 2, what we have to do is introduce all sources and find the short circuit current across AB. So what we used to do, we used to introduce all sources and find open circuit voltage across AB for the Thevenin's theorem. Difference is now we have to find the short circuit current across AB for the Norton's theorem. So what do I mean? Let me draw the circuit again. So we have 6 volts and okay, I'll draw it here. We have 6 volts, then we have 2 here, then again 2 here, and then this is 2 amperes. Now the load terminals A and B we have to short circuit, and then this current is the Norton's current, INO. Okay, so what is the Norton's current? Okay. So how do you find this Norton's current in this example? Okay. So there are several ways to find this, but let's simply use the superposition theorem. So what superposition theorem says? First consider each source at a time. So first take the 6 volt source. In that case, this 2 ampere, because it's a current source, it gets open circuited. So what will be the current? So I1 is 6 volts divided by total resistance will be 2 plus 2 series, it will be 4. So 6 by 4. 6 volts by 4 ohms. Okay. So in the case of superposition theorem, so that will be how much? So 6 divided by 4 is 1.5 amperes. This is I1. Okay, so what is I2? In the case of I2, you have to short circuit this the voltage source and only consider the current source 2 amperes. Now 2 amperes current goes up. Left side this is short circuit and this path has a resistance of 2 ohms, and right side also has a path of resistance of 2 ohms. So it is exactly symmetrical. So 1 ampere will go left and 1 ampere will go right, and it will flow through this. So therefore I2 will be nothing but 2 by 2. So that is 1 ampere. So now what will be the total current? So now we have INO, Norton's current. It's nothing but addition of these two. 1 plus 1.5, we have 2.5 amperes. Okay. So now I have Norton's current and I have Norton's resistance. So I can draw an equivalent circuit. How do I draw the equivalent circuit? Like this. So I have A, B as voltage, the terminals, and like this. So this is 4 ohms, this is RNO, and then INO, Norton's current, it is 2.5 amperes. Okay. So if I short circuit this, then the entire 2.5 amperes flows through that. So that makes the sense. Now if I want to find there is another question, find Thevenin's equivalent. So simply I use Ohm's law. V is I into R, right? So if I multiply these two, 4 into 2.5, that will be 10. Okay, so the Thevenin's equivalent will be simply 4 ohms and 10 volts. So this is my Thevenin's equivalent. Okay, so if I now, what is the proof? See, I just told you, simply use Ohm's law and then do it. So let us prove it. Okay. So how do we prove it? So the step 2 we will repeat. What is the step 2 here? Introduce all sources, find short circuit current. In our case now for Thevenin's, I'll find the open circuit voltage. Okay, so let me introduce, let me redraw the circuit. 6 volts, 2 ohms, then we have 2 amperes going up, and then I have a B terminals here. This is 2 ohms. Now analyze this circuit, and VTH is nothing but VAB is nothing but KVL from B to A. So KVL from B to A we have to apply. So let us look at this circuit. So this side is open, so here the current will be 0, here the current will be 0. So this entire 2 amperes will be going like this. So what is the voltage source here? 2 into 2, 4 volts. And this side will be plus and this side will be minus, because the current is going from higher potential to lower potential. So now apply KVL from B to A. So I started B, I go back, then from minus side I am going to plus. So I increase by 6 volts. So plus 6 volts. Then if I move forward, and then again from here to here I am going from lower potential to higher potential, increasing by 4 volts plus 4 volts. So that is 10 volts. So therefore VTH is 10 volts. So here, which is exactly what we got in our by direct formula also. So here we proved the Thevenin's equivalent, which can be calculated using the formulas. So this is the solution for the first problem. Okay. So now you got the idea how to apply. So now let us go to the second problem. Okay. So this is the second problem. So look at this question, and you can pause the video now and try to answer it yourself. Follow the same steps and then see whether you can find the Norton's equivalent. Okay, so now I will start my answer. Okay, so if you want to try, you pause now and try. My answer is like this. So first, step 1, find RNO equal to RTH equal to what? So what I have to do? All the voltage sources have to short circuit, all the current sources have to open circuit. So if I short circuit this, 15 and 10 will become parallel connection. Then 6 will be series with that parallel connection, and 4 will be series with that again parallel connection. So RTH will become 6 plus 15 parallel 10 plus 4. Okay, so what is, so if you want a diagram for this, let me draw like this. So this is 15, this is 10, this is 6, and this is 4, and this is A and B. So these two are parallel and series with 6. So we are all the time looking from the perspective of AB. So from A, if any current goes, first it goes here, then it goes through this, and then comes out like this. Okay, so what is this one? So 15 parallel 10. So 15 into 10 by 15 plus 10. That means 150 divided by 25. Okay, so that will be 6. So 6 plus 6 plus 4. 6 plus 6 is 12. 12 plus 4 is 16. Okay, so let me just confirm that. 15 into 10 divided by 25 plus 6 plus 4. 16. Okay, so I have 16 ohms as my Norton's resistance. Okay, now what is the next step? I have to find the current. Okay, so let us draw the equivalent circuit here. So step 2. Okay, so INO is what? Norton's current is what? See, you can also find the Thevenin's voltage first, and then from that you can find the Norton's current. Okay, that also you can do. But since we are starting with Norton's equivalent first, I am doing that. Okay, what I have to do, introduce all the sources back into the picture. So I have 20 volts here, and then 15 ohms here, and then 10, and then 6 here, and then a 4 ampere current, So now these terminals A and B I short circuit, and then this one I call it INO. Okay, so what is the INO current? This is what is our objective to find. So how do we find this current? So we have a circuit and we have what you call two sources. So I can apply superposition theorem and then find out. Okay. So let's apply superposition theorem. So in that case, what happens? First, let's consider this 20 volt source. I have to open circuit the current source. Okay. So if I open circuit this, then I have 6 and 4 will become series connected, right? If I open circuit this 4 amperes and 20 volts is only there, so 6 and 4 will be series, that is parallel with 10. So 6 plus 4 is 10, so 6 plus 4 will be series, that is parallel with 10, and this whole thing is nothing but 10 parallel 10, that is 5 ohms. Okay, so plus 15 is anyway outside in series it is there. So the effective resistance RE becomes this is 10 parallel 10, 5 plus 15 is 20 ohms. Okay. And the voltage is 20 volts, so 1 ampere current flows here. Okay, so I total is 1 ampere. I'm sorry, let me write 1. Now that 1 ampere is going here. Now this branch is not there, right? So this branch resistance is 10 ohms and this branch resistance is 10 ohms, exactly same. So 0.5 amperes will go through this one. So I1 is 0.5. Okay, so I calculated now I1 is equal to 0.5 amperes, because two parallel branches have the same resistance. Half current will go that way, half current will go this way. Okay. So now let's draw the circuit again, and this time I will consider only this 4 ampere current source. So I have 15 ohms here, then this is short circuited, then I have 10 ohms here, then 4 ohms here, and then 6 ohms here, and then this is a 4 ampere source, and then there is a short circuit here, and my objective now is to find this current INO. Okay, so what is this current? So here this 15 and 10 are anyway in parallel. So 15 parallel 10, what was it? So already we did that. So 15 into 10 divided by 15 plus 10, that is 25. So I got 6 ohms. Okay, so this branch is 6 ohms. 6 plus 4 is 10 ohms. Okay, so finally this circuit can be redrawn like this. So we have 4 amperes like this. Then there is a, let me 6 ohms resistance here, and then I have this is 6 plus 4, 10 again. Okay, so I have 10 ohms resistance, and here is where is our the required current that we need to calculate. That is the, basically I want this current INO. Okay, so this current anyway 4 is there, so current division principle will apply. So I2 here will be simply total current multiplied by opposite resistance divided by sum of the resistances, 16. Okay, so 4 into 6 by 16. Okay, so what is that? So 4 into 6 divided by 16, so I'm getting 1.5 ampere. So this I1 I2 I got, so the Norton's equivalent current will be 1.5 plus 0.5, so that will be 2 amperes of Norton current. So I have the Norton current here, and I have the Norton's resistance here. So now I can make the Norton's equivalent circuit, which is like this. So this is A, B, and this is 16 ohms, because here we calculated 16 ohms, and this current is 2 amperes. So from these two, what is the Thevenin's equivalent? So Thevenin's equivalent I'll draw here. So Thevenin's equivalent is nothing but 16 into 2, I into R. Okay, so 16 into 2 is 32. So 32 volts and 16 ohms. Then I have AB terminals. Okay. So this becomes the Thevenin's equivalent circuit. So but then is it correct? So let's prove it. Okay, so How do I prove it? How do I prove? Let me draw the circuit again. So here is the full circuit. Actually, I can use this diagram itself. I'll once again draw. So 20 volts, and then here 15 ohms, and then 10, and here 4, and here 6, and here 4 amperes. Okay, so let me bring it to the center. Okay, now you see here this is open circuited, AB is open circuited, and I want to find the VAB. That means apply KVL from B to A. So this 4 amperes will flow completely in this itself, in the 6 ohm resistance itself. So 24 volts will be the voltage here. Which side will be high voltage? This side will be high voltage, this side will be low voltage, because the current is going in this direction, towards the left. Meanwhile, here 25 ohms is the total resistance in this loop. Okay, so current will be V by R. Okay, so 20 divided by 25 will be the current. Okay, so what is that? 20 divided by 25. So 0.8 amperes. Okay, so 0.8 amperes is the current. Okay, so the 0.8 amperes current is going downwards. So now apply Kirchhoff's voltage law. So VTH is equal to KVL from B to A. So start at B. There is no voltage drop here because there is no current. Now you come up to here. So now I can go directly up. Now I am going against the current. That means my potential will be increasing. And 0.8 into 10 is 8 volts. So from here to here I gain 8 volts. So plus 8 volts. Again from here to here, again you see minus and plus. Again I am going against the current. So plus 24 volts. So what is 8 plus 24? 8 plus 24 is nothing but 32 volts. Okay, so this is nothing but your VTH, Thevenin's voltage, which is exactly what we also calculated. So here. So with this we finished the problem number 2. Okay, so let's increase our speed and then we'll keep going. Now, problem number 3, it says considering AB as a load terminals, find Norton's equivalent and find Thevenin's equivalent. Again, the same thing is given to you, so just find this thing. Okay, so how do you find? Okay, so how do you find the Norton's equivalent? Okay, so how do you find the Norton's? First, let's you can pause the video here and you try your answer. You try your method and you can compare with mine. So see, even if you get the correct answer, you look at, I'm going to use a different procedure for this. Slightly, I'm going to use my creativity in addressing this solution. So just have a look at it. It's going to be interesting. Okay, so what do we have here? Step 1. Step 1 is short circuit all the voltage sources. So 6 parallel 3. So 6 into 3 is 18, 6 plus 3 is 9, 18 by 9 is 2 ohms, and then 3 is in series. So RNO, Norton's resistance, is equal to Thevenin's resistance, which is equal to 6 parallel 3 plus 3, which is equal to 5 ohms. That is done. Step 1 is done. Now in step 2, what I want to do, let's mark these two terminals, okay, as let's say X and Y. Now look left side. This looks like a Thevenin's equivalent, right? Some voltage with series with resistance. This looks like a Thevenin's equivalent. So what is the Norton's equivalent of that Thevenin's equivalent? It will be nothing but V by R. So 30 by 3 will be 10. So this left side part I can replace like this. Okay, so I can say 10 amperes in parallel with 3 ohms. So those 2 points X and Y I said, that can be replaced like this. So here is the what I have drawn, this circuit. So what I have done is I split up this branch 30 volts into 3 as a equivalent Norton branch. Okay. Similarly, another branch is there, 6 and 15. So let us split up that into again its own parallel, its own Norton's equivalent. So I equal to V by R. So 15 by 6. Okay, so what is that? 15 divided by 6 is 2.5 amperes. Okay, so there will be a current source of 2.5 ampere. Here we should be very careful. Minus plus, that means positive terminal is this side, so the arrow should be pointing downwards here. The current source will go downwards, 2.5 amperes, and in parallel it has a resistance of 6 ohms. Okay, so now this and these two are connected like this, right, at these 2 points x and y. So I can now connect these two like this. Now on the right we have a 3 ohms and then AB is there, so we'll come to that. So let me put 3 ohms here, A is there and B is there. Now you see this is two current sources in parallel. Okay, so what you do if there are two voltage sources in parallel? So for example, let me take a rough sheet. So let's say you have 12 volts and 7 volts in series, two voltage sources. So this you can replace it like a 19 volt source. 12 plus 7 is 19, so 19 volt you will be doing like this, right? Or in other words, if you have like this 12 volt and 7 volt, okay, so in this case what you do, you will replace it like 12 minus 7 is 5, so 5 volts source like this. So you can add or subtract whatever depending on the direction voltage sources in series. In similar way, if there are current sources in parallel, you can combine them. Okay, so adding or subtracting them. So 10 is going up, 2.5 is coming down. If you merge these two, I'll get a single equivalent current source of 7.5 amperes going upwards. Now 3 and 6 are in parallel. So what is 3 parallel 6? 6 into 3, 18. 18 divided by 9, 2. So it will be a 2. Now I have 3 ohms here. So A, B. Now again looking at these two terms. So if I mark these two terminals as again X and Y, if I look at left side, there is a Norton's equivalent, right? So can I get a Thevenin's equivalent of this? Yes, I can get. So from here, the circuit becomes like this. I'll draw it here. So 7.5 into 2 is 15 volt. Okay, so I get 15 volts here, and I have two become in series. Okay, so 2 will become series and 3 is here. 2 is here and 3 is here. So now I have A and B terminals. So this ultimately becomes 15 volt in series with 5 ohms as a complete Thevenin's equivalent across the terminals A, B. So this is automatically your Thevenin's equivalent, VTH, RTH. Now once I get Thevenin's equivalent, I can also get the Norton's equivalent. What is the Norton's equivalent? So V by R is 15 by 5, 3 amperes. So I can have 3 amperes of current with 5 ohms parallel. So this is my Norton's equivalent. Okay. So what we have done, we have taken a completely different approach here. So we have taken the circuit and broken down into parts. Okay, so taking the first part of the circuit. So just to look at this first part of the circuit like this. So looking at left, this part, I can convert it into equivalent Norton. Then looking at only this part, 6 and 15, I can convert equivalent Norton. Those two Norton equivalents can be merged. Okay, so like this, a single Norton will come, and then that single Norton I converted back into Thevenin. So then I merged with this, then I got a final Thevenin, that one I combined to Norton like this. Okay, you may say, oh no, you are all doing this some random tricks. This is not the correct way. The correct way is, you find out. Anyway, so let's do it correct way. By the way, here you see the 5 ohms is exactly matching here also. Okay, so anyway, so what is the correct way, or what is the old way or slow way, or whatever, your way. Let's find out the first current in this. Okay, so Thevenin's voltage I will find out. How do I find? So what will be the current in this loop? So let me draw that again. Okay, so So or I will use this place. Okay, so find VTH. So how to find VTH? So here you can simply see that 3, 6, the circuit is like this, AB. So here this is opposite connected. Okay, so that means the positive of 15 volt is connected to the negative of 30 volt. That means these two voltages will add up, they are series. Okay, so total voltage in this loop is 45 volts, and only two resistances 6 and 3, they will be series, because this branch has no current, this branch has no current, so only one loop current is flowing across all this. So 45 volts, and then 9 ohms, 6 plus 3 is 9, so 45 by 9, what is that? 45 divided by 9, I get 5 amperes. Okay, so 5 amperes is the current here. Now if 5 amperes current is flowing, how to find VTH? Apply KVL from B to A. So I start at B, I'll go like this, I increase by 30, so plus 30, then from here 5 into 3, 15 volts, I am decreasing because I am going in the same direction of the current, so minus 15, so I get 15 volts as the Thevenin's voltage. Thevenin's voltage I have, Thevenin's resistance I have, so that is exactly what we also got, 15 by 5. So there are different ways to solve an electrical circuit problem. That's what makes this thing very interesting. So particular way will be very easy, particular way can be solved mentally. In fact, it can be solved mentally, right? So if you see 3, 30 and 3, so it is like a 10 amperes, and whereas this one is 15 by 6, so it's like a 2.5 amperes. So 10 minus 2.5 is 7.5 amperes, and these two parallel will be 2, so 7 2 is 15, and 15 2 3 is 5. So like that, you can actually mentally do all these steps, whatever is done, and we can find the answer. So anyway, I think I'm spending too much time on third problem anyway, because the methodology is different, so that's why I spent that time. Now let's go to fourth problem. Now fourth problem, again you can pause and check. This is the interesting thing, there are no numericals given, so just that find Norton's equivalent circuit in terms of E1, E2, R1, R2. Two EMFs are given, two resistances are given. So just how do you find Norton's equivalent? Okay, so we will simply find as a formula. Okay, so what I will do, already we learned one trick here, right? What is the trick we learned here? I can replace this with a Norton's equivalent, only this branch, and then only the second branch, and those two I can merge. So let's see what is the Norton's. So I'll have a Norton's equivalent like this. So R1, and this one will be I is V by R, so R E1 by R1, so E1 divided by R1. So this is one equivalent Norton of this voltage series with resistance. I can replace like this. Voltage series with resistance, again I can replace with another. Okay, so how I will be replacing? Notice these two are pointing upwards, positive, so the arrow also will be upward, and then I have R2 here, and this one will be E2 by R2. Now I have AB terminals. Now what I can do, simply I can go for a combined current source, which will have E1 by R1 plus E2 by R2, right? And then, so this is the entire value of the current source. Then I have a resistance, single resistance, that is nothing but the parallel combination of R1 and R2, so which is nothing but R1 R2 by R1 plus R2. So now this is what was asked, right? What was asked? Find the Norton's equivalent circuit. So this is the Norton's equivalent circuit. So just divide the voltage by resistance, voltage by resistance. Similarly here parallel combination, whatever is the total current, that is the Norton's equivalent. Okay. Now how do you find the Thevenin's equivalent? So simply I know, I you know, R you know, so you multiply these two. So a little bit of manipulation is needed. So but anyway, I leave it to you to try it, how to do that manipulation and get the Thevenin's equivalent. I'll skip the Thevenin's equivalent part. Yeah. I can do it, but let's skip it, it's not that interesting. So now come to the fifth problem. So remember this formula, E1 by R1 plus E2 by R2 is the total current, and then this parallel combination. Okay. So now look at the this thing. Here a load resistance is given, 3.6 ohms load resistance is given, and then the question is asked, find the current I. Okay, so what is the current I flowing from A to B? You have to find out. And if you see, this circuit is exactly same as this circuit, so both are same. Only thing is, here the load resistance was not given, here the load resistance is given, that is 3.6 ohms. So I will apply the formula. So what I will do, simply go for Norton's equivalent. Okay, so what is Norton's equivalent circuit? So I need one current source, and then I need one resistance, and then finally I have the resistance of 3.6 ohms. Okay, so this is A, B. Now what is this one? So according to the formula, here you can see we got a formula, right? E1 by R1, E2 by R2, and then this is. So what is that? 15 by 6 plus 10 by 4. Okay, so 10 by 4 is 2.5. 15 by 6. 15 by 6 is 2.5, and 10 by 4 is also 2.5. So 2.5 plus 2.5 is 5 amperes. So I got the current as 5 amperes. And 6 parallel 4. What is 6 parallel 4? So 6 into 4 divided by 6 plus 4. Okay, so 2.4 ohms. Okay, so I am getting 2.4 ohms as the this thing. Now finally, what is the load current IL? So load current is nothing but 5 multiplied by opposite current division principle basically. So IL is nothing but 5 multiplied by 2.4 divided by 2.4 plus 3.6. Okay, so what is that? So 2.4 plus 3.6 is 6 actually. So 5 multiplied by 2.4 divided by 6. So exactly 2 amperes I am getting. That is the answer. Okay, so in this 3.6 ohm resistance, 2 amperes current is flowing. Okay. Now how did you solve it? So here we used, very interesting, the formula based and all. But there are several ways to solve it. You can solve it using superposition theorem. Consider 15 volts at a time. In that case, 10 volts will be short circuited. 4 and 3.6 will be parallel. All the things you can do. That is considering 15, considering 10, and then that is a superposition theorem way. Next, you can do Thevenin's theorem. What is the Thevenin's theorem? You open this circuit and then open the load resistance, find the Thevenin's resistance, then what is the loop current, then what is the voltage, apply KVL from it, all that. Rather than that, in Norton we got it more easily, more simply, more less effort. Okay, so in that sense, sometimes the more theorems the more it's like when you want to go from one place in the city to another place, if you know only one route, then you on that route, if there's any traffic jam or something, you should be able to divert and then go in another route to reach your destination in a faster time. So if you know different methods, different techniques, you can do that. Anyway, so now let's come to the final problem on for this particular video. Maybe in future I'll make more videos on Norton's circuit, but anyway, look at this circuit. Try to use your whatever intelligence and knowledge you gained and try to solve this particular thing. So what is the question? Find Norton's equivalent circuit between the terminals A and B. Find Thevenin's equivalent circuit between terminals A and B. So how do you do it? Okay. So you can go ahead and do it now. Meanwhile, I will solve it in my own or whatever method, and then we'll compare your answer with my answer, whether our Norton's equivalent is matching or not, and whether our Thevenin's equivalent is matching or not. So let's do that. Let me start. Again, I strongly ask you to pause this video and try if you have not tried it. So then your understanding can be verified, but otherwise let's do it. Now here you see 2 and 4 are in series. So 2 and 4 in series means it will become 6 volts, 6 ohms and 6 volts. So I can replace this branch, this entire branch with 1 ampere in parallel with 6 ohms, right? So this is the what happens for the left side. Now this branch 18 and 6. Now here you cannot add 4 because there is a split here. There is another branch going that side. So only you consider these two. What is that? 18 and 6. Okay. So what is the current? V by R. 18 by 6 is 3. Okay. So here I have, again, be careful with the arrow. So both voltages are positive up. So my arrow is correct. So again there is a one more 6 amperes. So far I completed this part of whatever I covered with this paper. So this part I have completed. So I'm sorry. So this part is completed. Now I have 4, 3 and 6. So anyway, 3 and 6 I can, it doesn't matter. So I can simply make it into a 2 ohms resistance. Okay, so I have a 4 ohms here and then I have a 2 ohms here. So again 4 and 2 are not series as of now because of these terminals A, B that we are interested in. So next, now what we can do, see these two are in parallel. So this can be added to 4 amperes. This is 6 ohms. Now 6 and 6 are in parallel. So that can, but 6 and 2 are not in parallel because in between this 4 is coming and disturbing the thing. Okay, so this can be replaced with the 4 ampere current source in parallel with the 3 ohms resistance, and then here 4 ohms is the resistance and here it is 2 ohms, and finally I have the terminals A and B. So now again you got the idea what I can do. This Norton's equivalent on the left side of this 4 and 3, so that can be replaced. So 4 into 3 is 12. Okay, so it is replaced by like this 12 volts. Okay, and then in series with 3 ohms, which is again in series with 4 ohms, which is again in parallel with 2 ohms. Finally I am getting A and B. Okay, so here what I can do now, 4 and 3 are in series. Okay, so it becomes 7 and this is 12. Okay, so again I will find the equivalent current for that. Okay, so I is V by R. Okay, so 12 by 7. So 1.714. Okay, so anyway, whenever I see like decimals like this, I get a doubt. So let's see. So this is my circuit now. Now again this 7 and 2 are in parallel. So 7 into 2 divided by 9. So I'm getting 1.555. So 1.714 amperes, 1.555 ohms, and I have my AB. So this I claim as the Norton's equivalent circuit. And once we have the Norton's equivalent circuit like this, then it becomes the Thevenin's becomes the easy way to solve. So Thevenin's will be simply 1.74 into 1.555. So you will be getting that. Okay, so again try to solve this yourself using some different method, and then try to see whether your answers matches with my answers. So this has been a kind of a full lecture, 45 minutes to 50 minutes lecture on Norton's theorem, where the entire circuit can be replaced by a single current source in parallel with a resistance, and we have solved multiple problems. And the idea of solving these problems was to give you some kind of tricks and some kind of techniques which you can use to analyze the circuits better. So I think with this we will conclude this video here. Again, search online, simply go to Google search and find Norton's theorems example problems. You will find many example problems online. Note down maybe 5 or 6 example problems in your book, and then try to solve it like this, and then check your answers with what they have online, so that you can confirm your learnings. So if you like this video, please press the like button, and please subscribe to my channel and refer my channel to your friends, so that they also can be benefited. So with this I'll end this video here. See you in some other video. Thank you.